Hello everybody, my name is Anil Kokaram. I am the head of Department of Electronic and Electrical Engineering here at Trinity College Dublin. And what I'd like to do today is just highlight for you our offerings across the three streams in electronic engineering all the way across to computer engineering. Perhaps it's best if I describe this as a continuum from electronic system design all the way across to software system design. We offer this continuum manifest in three streams: electronics, electronic and computer engineering, and computer engineering. And the streams and programs are jointly created by the School of Engineering and the School of Computer Science and Statistics. I am the head of electronics, so I'm going to say a bit more about electronics and electronic and computer engineering. So in our experience, you are most likely to want to know one of three things, right? What is the career prospects in this discipline? What is electronics engineering anyway, and how good is Trinity College in that area? And what's actually in the course once you get here? So to answer the first question, electronics and electronic and computer engineering, that entire continuum of technology has been and will remain a vibrant area for career development. And there are certainly a huge amount of jobs across the Irish technology sector. This year, a company called Xilinx, just here on our doorstep in Dublin, was acquired by AMD. And it's a fantastic development for the Irish technology sector. Now we have a major new competitor for Intel right on our doorstep. These two major competitors in the CPU market are now based here in Ireland. We have Movidius, which was a startup acquired by Intel a few years ago. Many of our electronics engineering graduates work there. A huge new development. Qualcomm and Quark first arrived here about 4 years ago, and they've been hiring aggressively ever since. Qualcomm, they make almost every single electronic component in your mobile phone. And as it turns out, there are many significant parts of Google and YouTube which have electronic engineers from Trinity College. The impact of electronics design has extended even to places that you wouldn't think. So, as you might know, there are more sophisticated electronic design components in cars nowadays, and Jaguar Land Rover is the latest in a string of manufacturers who have moved a lot of their electronics and computer engineering development work across here into the west of Ireland, and they've been here in Galway for several years now. So there's no lack of jobs in the sector. The hiring has been aggressive even through the pandemic, and all of our graduates got internships and jobs even through the pandemic. As far as Trinity College reputation is concerned, well, we remain at the top, the best in Ireland for electronics engineering and certainly computer science. And the degree program is accredited by Engineers Ireland. We are now constructing a very fantastic new facility for undergraduates called the E3 Learning Foundry, which will be specifically for undergraduate teaching, and that will launch in a couple of years. We remain very strongly connected to the international industry sector. In fact, you may not notice, but YouTube and Google use technologies that we developed here every day. So the enhancement technology that was developed in our video processing laboratory is used in YouTube, and movies also use our enhancement technology every day in post-production. And these are some examples of the movies in many years ago that used this technology. Now, it must seem very strange for an electronics engineer to be talking about such a wide range of applications and careers. So I just want to sort of dig a bit deeper and highlight the fact that the reason why this has happened is because of the prevalence of information processing, right? So many years ago, it was discovered that if we convert measurements into a digital signal, then we have a much more flexible mechanism for using those measurements to control machines, predict events, enhance experiences, and so on. And it is since the 1960s that idea of digital processing has changed the way we build systems and now impacting so strongly in the way that we work that it is a kind of new industrial revolution. So this idea of information processing has pervaded a lot of our modern life, and electronics and computer engineering is sort of at the heart of these new developments. I just want to sort of bring to the surface more an interesting example of that, which you might not realize, and which shows sort of the different layers in the way we think about problems today and how that might involve electronics somehow. So here are 3 frames from an archived motion picture sequence, and you can see that the middle frame has a bunch of black splodges on it, and that's called dirt, right? This is actually digitized film, and the problem with digitized film is that it tends to look like this, and it's very difficult to remove this defect manually, and it's an important defect to remove because then we could broadcast it on a digital medium and improve the quality for more consumers to enjoy more efficiently over the internet. So how do we actually solve this problem? How do we detect and then remove these missing splodges, let's say? So it turns out that by modeling this signal and by thinking about pictures as pixels, so here, for instance, these little splodges are black and these are bright, and I could see that in a image sequence, things don't change much from frame to frame. So anything I see here, which is very different in subsequent frames, I could say is a problem. Thankfully, when I digitize pictures, they consist of just arrays of numbers. So this turns from a measurement problem into an algorithmic mathematical problem. So if I could detect patches of numbers, of colors, which are different from subsequent frames, then I could probably do a good job of automated detection. It turns out that the complicated thing here is that things move around, so change happens as a natural course of motion. So I have to get a bit more sophisticated. So here I'm using a machine learning technique to estimate motion, and these are the directions of motions into the future frame and into the previous frame. And here I am measuring forward and backward differences and making decisions as to whether certain pixels are corrupted or not. And here I am coloring in white pixels which I believe to be corrupted and those which are okay. So this process is doing a reasonable job of finding all the missing holes, and the next step is trying to figure out how I am going to interpolate or fill in those missing gaps. And in a way, what I've been describing there is an algorithm for automatically detecting splodges or dirt in a movie. And so we sort of talked about how to model the signal and how to use the fact that pixels don't change much in color from point to point. We use that to predict what the signal to look like. Then I could classify pixels as missing or not, and then I could use that model to reconstruct the data in those parts. Now the thing is, I could implement that algorithm in hardware or software, and it turns out that depending on the amount of consumers that want to use this product, I might have to do one or the other. This is like one example of this huge area of machine learning and digital signal processing, and more recently, deep learning. And just to give you an idea of what can be achieved, here on the left is an example of an archived film from 1910, digitized and stored in the Irish Film Centre. And on the right is automated restoration using some of these ideas. There are other things going on here. de-shaking, for instance. On the right, it's more stable, and on the left, you could see some enhancement of edges, line scratches also removed. A lot of other things going on here, a lot of other algorithms being used to do this automatically. Now, just to show you how we can go from this, what would appear to be an esoteric research problem, to something which you see every day. In fact, this sort of treatment is used in film for cinema post-production quite a lot, and this became so popular that by around 2007, it was being used by a lot of engineers in cinema post-production houses, and these are some examples of the movies where that technology was used. And in 2007, myself and a few of my colleagues won an Academy Award for this work, which is quite an amazing and strange thing for an electronic engineer to say and be involved with. And usually when I say something like that, people want to see some evidence. So here are some pictures that we took on the night. It's a long time ago, and these are my colleagues on the 79th Academy Awards. And there's a picture of me way up there, and that's the closest I ever got to somebody famous. So I guess the point I'm trying to make here is that entertainment drives technology and has been driving technology since 2000. The fact that right now graphics chips are used in heavy computation, not only for the entertainment sector, but at the health sector, is because of the push for more computation to enable things like real-time gaming over the internet, using a phone for watching movies. All of these things require the interplay of a number of different technologies, of which electronics and computer engineering is just one of these components. What has become very interesting in the last 4 or 5 years is that these applications have become so popular that software can't keep up. So it's now all about hardware and efficient, low-power designs once more. So all of these big companies, Google, Facebook, Apple, have hardware teams working on media engineering and computer architecture, and thinking now about the energy consumption of software, so that they're trying to build more efficient hardware to do things like video compression and so on. At the same time, electronics device technology has become so efficient and ubiquitous that sensors are cheaper and more reliable than ever. And nowhere is the impact seen more than in health. And in fact, in electronics engineering here in Trinity, we are hosting a company called Capri Medical while they develop new implants that suppress pain by sort of direct intervention with your nervous system, which is absolutely amazing development. Companies like Boston Scientific in Ireland, out in Galway, are also heavily involved in this interface between electronics and bioengineering. So let me say something about the course, right? When you get here, this is a general engineering course. So the first 2 years, you do aspects of civil engineering, mechanical engineering, electronic engineering. And then in third and fourth years and fifth years, you start to specialize more and more into one of these streams. So in the third year, you choose to specialize in electronics, or all the way across to system software development, or some mixture in between. And by the fifth year, you go on to do a master's program. Right now, we are trying to finalize our new development so that in year 3, you could apply to complete year 5 in Columbia, New York. And that's still a plan in progress. But my hope is by the time you graduate, you will have the opportunity to do this. Now, in the fourth year, you are given an opportunity to engage in internships. So here are a few examples of companies who we're working with and our students take internships with. This also happened through the pandemic. SIG is a great little company doing high-frequency trading on the stock market. Would you believe they require electronic engineers to design circuits to allow fast communications? Qualcomm, like I said, out in Cork, taking interns every year for development of new low-power circuits for mobile phones. And these are just a few of the companies that we work with across both electronics engineering and the computer science, School of Computer Science and Statistics. The curriculum itself, well, when you get here, we have a number of different aspects that you're exposed to. Remember, the first 2 years are general. So in the first year, we actually expose you to a number of technologies, not only in science and technology, but also in the arts. So we have some contributions from the music and media technology group who talk a bit about the impact of entertainment on technology and vice versa. Here on the bottom left, you can see 2 examples of our first year cohort designing a temperature sensor, which they then use to measure how concrete solidifies over time in a collaboration with the civil engineering department. This is a key point about this general engineering degree throughout, not just the first 2 years, but in particular the first 2 years, you are engaged in projects which allow you to taste all these different aspects. And this is a really good example where you work with the civil engineers to design a small piece of a concrete beam. And with us, you design the sensors that allow you to measure how that beam changes as it cools, as it solidifies over time. As you go on in the course, you specialize more and more. In 2017, we had to respond very quickly to a massive change in electronics engineering and signal processing with the arrival of this new era of deep learning. And we were the first to launch a course offered to undergraduates in deep learning, and that gives our graduates an edge. In the second year, just to highlight our connection with industry, we are very privileged to have Oliver James, who is one of the chief architects of an amazing effect that you would have seen in the movie Interstellar. He is the chief scientist of a company called Double Negative in London, and he helps us teach you about differential equations using his actual work in that movie. And we could draw a straight line between his work in that movie and the exact equations that you look at during this course. And in fact, during the course, you experiment on problems related to that movie effect. Here is an example of another second year project where you are designing an autonomous vehicle, and on the left is an example of the vehicles that you design as they follow a track around a small whiteboard, and increasingly sophisticated challenges met as the students, as you go through that second semester. On the right is some students having some fun. Late in subsequent years, we keep developing this project over and over to make it more sophisticated. And as you can see here, some students are trying to carry a substantial weight on that buggy. This, in the last couple of years, we have been able to give every student a design kit, which they experiment on themselves to build their own autonomous vehicle, and it is able to navigate a number of obstacles around the room without using that track. In the third year, like I said, you specialize more and more. This is some examples again of project work. Here somebody is demonstrating the use of software to design hardware, and in this case you're designing a clock, which an LED interface to display the readout from the world reference clock. And this requires some knowledge of digital circuit design, analog circuit design, and some amount of FPGA reconfigurable hardware. In years 4 and 5, we have had to respond, like I said, quite rapidly to major changes in our discipline. So we were the first to launch this deep learning course, and students actually challenged throughout the course to teach a machine to achieve certain goals, like to drive that car in a car simulator and so on. And you could have a look at that website to see more about that course. We have a number of research projects that you're able to take in the fourth and fifth year. In the fifth year, you can take research projects across the entire engineering disciplines, from civil to mechanical to electronics. Even if you do a project or choose the electronics discipline, and this sort of project actually exemplifies why general engineering is so important, right? So here's Stephen Roddy demonstrating some hand gesture drone control, and that project took place several years ago, and it actually has now led to a new course on cyber physical systems, which our fifth-year project students, or so fifth-year master's students, are engaged with right now, in fact. So this was actually just a short clip taken of students working on this course just about a week or 2 weeks ago, and you could see them developing the hardware for building the hardware for that drone, and actually making that hardware sensitive to motions. And you could see the hardware or the drone responding to rotations and translations of that small control that the student is using. And they are going on now to build more autonomous subsystems into that drone system. And this is a great example of a junction between mechanical and electronic engineering that we are exploring more and more in the future in our training programs. So I hope you get a sense of how electronics spans that gamut from electronic system design on one end all the way to software systems at the other end. So we have computer engineering on one end and electronics hardware on the other end. And in between, we have this electronic and computer engineering. These are some sites that you could look at for more information. The MIDAS site and that YouTube link gives you some very good background on how the electronic sector has evolved in Ireland, and how it's relevant, how that discipline is relevant to your career development now. So thank you very much for your attention, and I hope to see you in Trinity